Hello everyone and welcome back to Keeping Tabs on Chemistry. In this video we're going to be discussing vapor pressure. We're going to start off by reviewing what we know about states of matter. So there are three basic states of matter. At the very top we have gases. Gases have atoms or molecules that do not interact with each other except for when they collide. So gases are kind of a class all their own compared to the other two, liquids and solids. Liquids and solids are condensed matter. Their atoms or molecules are closely packed and do interact with each other regularly. So looking at a solid, we can see that a solid has a well-defined shape and volume. Now the molecules are still moving because remember all atoms and molecules are in motion, but they're very closely packed and don't have a lot of freedom. Liquids have a defined volume but no defined shape. They take the shape of their container, and they are much more free to move and slide across each other, which is what makes liquid mobile. Gases have no defined shape or volume. They will spread to fill whatever container or space that they are in. They have the most motion, the most freedom, and the least amount of interaction with each other. So, pressure. Pressure is the force applied over an area. So in terms of chemistry and molecules, it is collisions that cause pressure. When an atom or molecule hits the wall of its container, that is a force over an area. So collisions of molecules with their container causes pressure. There are four standard units of pressure. They are atmospheres, torr, millimeters of mercury, and kilopascals. We're going to dive into how we got each of these units, where those numbers come from, and so on. So for right now, no, we can do conversions with these units of pressure. One atmosphere is 760 torr, which is 760 millimeters of mercury, which is 101.3 kilopascals. So our first and SI unit of pressure is the atmosphere. Atmospheres come from the pressure exerted on the Earth at sea level from a 1 meter squared column of air. Thinking about if you were on your floor right now to put a square metered box, right? So 1 meter by 1 meter, so on. The pressure of the air of the atmosphere pushing down on you at sea level is where we get one atmosphere from. Now, we can use a device called a barometer to measure pressure. Barometers measure pressure in terms of how far a liquid is pushed up a tube by atmospheric pressure. So you have a dish, which in this case is filled with mercury, and then you have a capillary tube dipped into it filled with some of that mercury. So as atmospheric pressure pushes down on the mercury in the dish, it's pushed up the capillary tube. So different liquids move differently, but for mercury, which was the standard in barometers up until very recently, the height it was pushed up to at 1 atmosphere was 760 millimeters up this capillary tube, which is how we got 1 atmosphere equal to 760 millimeters of mercury. Now, torr is an interesting story. There was a scientist named Evangelista Torricelli. He decided to rename the units of millimeters of mercury to torr in honor of himself. And the name ended up sticking, so we actually recognize both, and that's why the number is the same. It was just renamed in honor of this chemist. So 1 atmosphere is also 760 torr. Now, in physics, you will learn that newtons are the SI unit for force. Since pressure is force over an area, so newtons over meters squared, pascals are what we rename that unit as. So 1 pascal is 1 newton per meter squared. So 1 kilopascal is 1,000 pascals. So when we actually calculate the unit of force that that column of air is pushing down on, 1 atmosphere is equal to 101.3 kilopascals. And that's how we get all four units of pressure. Now, the properties and behavior of matter will change with temperature and pressure. So, scientists needed to define a standard set of conditions to use as a reference for all these different properties. So we call this standard temperature pressure, or STP. So we have a standard temperature and a standard pressure. It is 1 atmosphere and 0 degrees Celsius. Now, Celsius is not always the unit of temperature we want to use in chemistry. We will also use Kelvin. So remember, to find Kelvin from degrees Celsius, we add 273. So standard temperature in Kelvin is 273 Kelvin. Also recall, Kelvin does not use degrees. It is just Kelvin, not degrees Kelvin. So before we can talk about vapor pressure, we're going to want to talk about volatility. Liquids are a condensed form of matter. So it forms when particles start to clump together. So liquids have less kinetic energy than gases. So liquids have more attractive forces, more intermolecular forces than gases do. These intermolecular forces are going to affect the physical properties of liquids. One of those properties is volatility. Volatile liquids are ones that readily evaporate, so evaporation is very quick. Volatility depends on the strength of attractive forces between the particles of a liquid. So, strong attractive forces between particles results in very low volatility. So, if I have strong attractive forces, I don't evaporate well, whereas weak attractive forces result in high volatility. So what this tells us is attractive forces must be broken in order for a substance to evaporate. Think about it like a jailbreak. If you're in a high security prison, right, strong attractive forces, it's not very easy for you to escape. Similarly, strong attractive forces means that the liquid particles can't escape to become a gas, to evaporate. Whereas, and I hate making this analogy, if you're in, a county jail, it must be much easier to escape and get out because the security isn't as strict. So weak attractive forces means high volatility. So here are 3 particle diagrams. You should be able to tell by how much has evaporated into a gas which one is the most volatile, evaporates most, and which one is the least. Take a moment and look at it. Okay, so the one that is most volatile is the one that has the most molecules of gas. So looking at this, I've got 1, 2, 3, 4, 5 versus 1, 2, 3, 4, 5, 6, 7, 8. So the one on the right is the most volatile. The least volatile is the one in the middle with no gas. So here's another question. Which one of these has the strongest intermolecular forces? That'll be the one that's least volatile, the one that sticks together more than it breaks apart. Now we can discuss vapor pressure, what it is, how we get it, and what it means. Now remember, pressure is the force exerted on a container, and collisions cause pressure. So vapor pressure is the pressure exerted by a liquid vaporizing, right, or evaporating. So if I were to take a liquid and put it in a closed container like this bell jar, right? So think about having a glass of water and you cover it. In a closed container holding a volatile liquid, meaning one that will evaporate, the volume of the liquid is found to decrease and then level off. So we're going to talk about why that happens. So the decrease in volume results from some of the conversion of liquid to gas, right? If you think about it this way, if you leave a glass of water on the counter overnight or for a few days, eventually all of that water is going to evaporate away. But if you close the container, okay, not all of it will evaporate. So the conversion of liquid to gas continues until an equilibrium is established between the liquid and the gas phases. Now, this equilibrium does not mean the conversion of liquid to gas has stopped. It just means that the rate of evaporation equals the rate of condensation. So I'm becoming a gas just as much as that gas is returning to becoming a liquid. And that only happens because it's in a closed container. So here's a diagram of what we're seeing. We start with a liquid that is going to be evaporating, evaporating, evaporating. Now, some of it recondenses, but my rate of vaporization is much, much higher. But eventually, I kind of run out of room in my container. At that point, the number that are evaporating equal the number that are recondensing, and I've reached an equilibrium, so this volume will no longer change. So equilibrium vapor pressure, we sometimes use equilibrium vapor pressure and refer to it only as vapor pressure. Since a gas is present in the closed container, the collisions of those gas particles with the walls of the container result in a pressure being exerted. Now, we use equilibrium vapor pressure as our standard vapor pressure because it is only going to be constant when it's at equilibrium. If I tried to measure vapor pressure when I originally put the liquid into this closed container, it's actually going to keep changing until I've reached that equilibrium and it has leveled off. Right? Because it's based on the number of particles that are colliding with the wall, if the number of particles is changing as more and more evaporates, my vapor pressure changes. So when we're talking about vapor pressure, we mean equilibrium vapor pressure. So, vapor pressure is measured using something called a manometer. A manometer is similar to a barometer, but instead of having an open dish on one end, we have a closed container with our liquid in it. So, we're looking at a bit of a battle between the pressure from my liquid and an open end with my atmosphere. So, here, once I've established equilibrium, I can see that these liquid molecules are pushing on this more than the atmosphere. So the difference between these two heights is my equilibrium vapor pressure. And I can measure that in millimeters of mercury or whatever substance ends up being in here. But we would want to use mercury because I can convert that to the other 3 units of pressure. So, vapor pressure and its relationship to volatility. Vapor pressure depends on volatility. The more volatile a substance, the greater the equilibrium vapor pressure. Since volatility depends on the strength of attractive forces, well, so does vapor pressure. So here's the idea. The more volatile a substance, the more molecules I am going to have as a gas, right? It has readily evaporated. There are more gas molecules. More gas molecules means more collisions with the wall. More collisions means greater pressure. So the stronger the attractive forces, right? The stronger the attractive forces, the less volatile I am, which means I have fewer gas molecules. So strong attractive forces means lower vapor pressure, right? Less molecules colliding with the walls will lower the pressure. So vapor pressure and attractive forces are inversely related. Now, volatility isn't the only relationship I have to worry about. Vapor pressure also depends on temperature. As temperature increases, equilibrium vapor pressure will also increase. Now, why this happens? As the temperature increases, the liquid particles increase in kinetic energy. Now, if I have more kinetic energy, I am able to weaken the attractive forces. It's a matter of time. If I am moving faster, I'm less likely to interact with my neighbors than if I'm moving kind of sluggishly and slowly. It's much easier to have a conversation with someone if you're walking by each other than if you're running in opposite directions by each other. So, higher kinetic energy, meaning higher temperature, means weaker attractive forces. The weaker the attractive forces, the more particles go from liquid phase into the gas phase. Remember, more gas particles means more collisions, means higher pressure. So, when does boiling occur? Boiling is defined as the point where vapor pressure equals atmospheric pressure. This is very interesting for us because we can do some really cool things with boiling. Now, in our everyday lives, here we are, we're gonna make some pasta. We go into our kitchen, and what do we do to get the water to boil? Well, to get the water to boil, we raise its temperature. So by raising its temperature, we're weakening those forces to increase the vapor pressure. So what we're doing is we are raising the vapor pressure to meet the atmospheric pressure above the pot. I can't exactly change my atmospheric pressure here in my kitchen. Well, maybe I can, but you guys can't. uh, so that is how we end up doing boiling. But this is not the only way to make something boil. If I don't want to raise the temperature of my water, I can make it boil by lowering atmospheric pressure down to where my vapor pressure is. You can do this a couple of ways. The first way, if you're not going to change your location, is to use a vacuum or a vacuum pump. Your regular household vacuum won't do it. So you could create a vacuum with a vacuum pump that removes air from your closed container, and you would end up lowering the atmospheric pressure down to the vapor pressure, and you can boil water cold. So at room temperature, I can make that water boil. The other way that you could do that is to actually change your altitude. So in Denver, Colorado, where there is less atmospheric pressure, they're at a higher altitude, which means less air is on top of them. They actually, when they go to boil water in their kitchen, their water doesn't boil as hot. The reason why is because it takes less energy for that vapor pressure to meet the lower standard of the atmospheric pressure. So they actually um, don't get as hot of boiling water. It's less than 100 degrees Celsius. That's actually why some boxes you'll see have different cooking directions based on your altitude. They'll say, cooking directions for in Denver or wherever it is, you need to cook things longer. You need to cook them longer because you're not cooking them as hot. So it's actually to our benefit to be at sea level where water will boil at its normal 100 degrees Celsius. Okay, so vapor pressure graphs. On a vapor pressure graph, you're comparing temperature and vapor pressure. So looking at this, it's asking which compounds have the strongest intermolecular force. So between all four of these, if you were to pick any given temperature, say we'll do 60. 60 here. Ethylene glycol has a very low vapor pressure, then water, then ethyl alcohol, and not even on the chart we have diethyl ether. So, if at the same temperature I have high versus low vapor pressure, strongest intermolecular forces means that I'm not going to be able to escape to become a gas, which means I'm not going to have collisions, which means I'm going to have a low vapor pressure. So the strongest intermolecular forces are the one that's farthest down, or the one, if you think about it vertically, farthest to the right. That's the ethylene glycol. So what is the boiling point of ethanol? Remember, boiling occurs when the vapor pressure, this line, equals the atmospheric pressure. Now this is in torr, so atmospheric pressure is 760. That one atmosphere is 760 torr. So I'm looking for where these two lines meet. So here's ethanol. Where it meets 760 is 78.3 degrees Celsius. Now I can draw a conclusion here. The stronger my intermolecular force, remember as I go from left to right, the stronger the IMF, the higher the boiling point. So that's another relationship I can draw. All right, there's a practice. The first two questions are pretty easy. The last one might give you some trouble, but go ahead and try. Pause the video when you're ready to hear the answers. Unpause. Okay, so looking at the first question, what is the boiling point of CCl4? I need to find where the vapor pressure line for CCl4 equals atmospheric pressure. Now this is in kilopascals, so atmospheric pressure is 101.3. So where these two meet, I'm going to estimate about what temperature that is. You should have gotten around 75 degrees Celsius. If you got 74, 76, that's fine. Remember, we're estimating that last digit. Which compound has the strongest IMFs? That's going to be the one farthest to the right, which in this case is water. Now that makes a lot of sense for me, because looking at this, water has hydrogen bonds. Makes sense for that to have high intermolecular forces. And then will CaCl3 boil at a temperature of 50 degrees and a pressure of 60 kilopascals? This is a difficult question. So if I think about it, at 60, if my atmospheric pressure is 60 kilopascals, right? So atmospheric here is now 60 kilopascals. It's going to meet CH3Cl. It will boil at this temperature. So I come down and I see that that is about 45 degrees. So if it boils at 45 degrees at that pressure, and I'm at 50 degrees Celsius, then yes, I will be able to make my CHCl3 boil because I'm above the temperature threshold that I need to be at. Tricky question, but worth asking. Okay, that concludes our lesson today on vapor pressure. I'll see you next time.